So now that we looked at SN2 and SN1 reactions, we're going to be looking at E2 and E1 reactions, and these are known as elimination reactions. So pretty much what an elimination reaction is it's going to be creating a double bond, okay? So we're going to be looking at E2 first, and we'll see the mechanism will look something like this. So what happens is, every single time we're always going to have this H, and we're going to have a leaving group. It could be a halogen, it could be whatever. And so what's going to happen is the electrons from the hydrogen are going to bond to make the alkene, and the leaving group is going to leave. So we're going to see that the product is going to look something like this. Okay, so notice how I put it in a cis conformation or a Z conformation. Okay, so there's a reason why we did that, and we're going to see that right now. Okay, once you can get the hang of it, you don't have to draw this, but we're going to be drawing a Newman projection. Okay, and it's going to be viewing it from this side. So this is a good practice even for just drawing these Newman projections. So it's going to look something like this. Okay, we see that from looking from this side, we have on the outsides we're going to have these ethyl molecules, and we see that right there. And we know this is one key point. The H and the Cl, so the H and the leaving group, always have to be anti from each other. So they have to be in the anti-conformation, and that's very important for E2. That's something you have to remember. If there's more than one hydrogens, that is when it will come into play, and we'll need to see that later on. But what happens is the hydrogen and the Cl have to be in anti-conformations before we can even have this go into E2 mechanism. Okay, so because of that, we see that if we were to form this right here, we would have on the top, we would have this ethyl group right here, and we would have the ethyl group on the same side. So because in the Newman projection the ethyls are on the same side, we see that they also have to be on the same side in the alkene molecule. Alright? And we'll see that that's very different from in the E1 mechanism. So in the E1 mechanism, similar to the SN1, first step, leaving group. Alright? So we're going to form this carbocation right here. So that has left, and what's going to happen now is we're going to have this H2O go, and similarly to E1, now attack and bring it down. Okay, so we're going to see that the product is going to look something like this. And notice nothing really changed. You know, the molecule looks exactly the same. Why did I draw it differently? Why did I draw it in the trans conformation? Well, the one thing about E1 that we need to know is that trans is more stable than cis. Okay. And that's in any type of alkene. Trans is always more stable than cis, right? Because they stack. Because they stack, it'll be more stable, and so we're more likely to see trans over cis, right? And so that's the reason why E1, I drew it in the trans conformation, because of the stability, right? So E2 anti-conformation will determine whether or not it's cis or trans, but in E1, we're always going to see that trans is going to be more stable. And that being said, cis, even though it's less stable, doesn't mean it's never going to show up. It's just going to be in the lesser amount. And so now that we kind of had the mechanism down, we're going to be looking at the facts previously like before. So E2 is called bimolecular elimination versus E1 unimolecular elimination. And remember, just like SN2, the reason why is because of the rate. So the rate in here is dependent on the nucleophile and the electrophile versus just the electrophile in E1. And that's why we get this unimolecular, just the electrophile. And so the reactivity of them is going to be tertiary is greater than secondary is greater than primary, and the same goes for E2 and E1. And this is different from what we saw in SN2 and SN1. Remember, the E2 was reversed. And the reason for this is just that simply because alkene molecules are more stable with more groups around them. We remember that from before when we talked about alkenes. So tertiary is greater than all the way to primary. Okay, so these are just kind of some interesting facts or things that key points that we need to know. E2 is a concerted mechanism. It happens in one step, versus E1 forms a carbocation, so it's a two-step reaction. E2 also needs that anti that we talked about before. E1 is trans versus cis, so that's what determines the stereochemistry. And for E2, we need some good, strong bases. Okay, versus E1 needs poor nucleophiles. Okay, and that's one thing I didn't mention before, is that E1 couples SN1. So a lot of times when we have SN1 reactions, we're going to have E1 as another product. Okay, and so that's why we see that poor nucleophile similar to SN1 reaction. Okay, so we know what poor nucleophiles are, like H2O or alcohol. What's a good strong base? So some good strong bases are like OH minus, tert-butyl, OCH3 minus, stuff like that. Okay? And so for the solvent, it's the conjugate acid of these bases. So for example, if we had OH minus as our nucleophile, the solvent would be H2O. If we had that tert-butoxide, solvent will be like that. Okay, so you guys get the hang of that. And for this one, E1 is just protopolar, and we would learn that before, something that has hydrogen bonds. Okay, so like H2O, alcohol, stuff like that.